Hey, welcome back. In this video, I will share what are Bohr's atomic model postulates. I will explain the existence of energy levels in an atom and how to calculate energy of an electron in a permitted orbit, and also the formula involved, such as energy of a photon, energy difference, and also the wavelength of photon due to electron transitions between energy levels. I am Teacher Tan. If you like my videos, do remember to click on the subscribe button below so that you won't miss any notifications when I update my channel.
In the mid of 18th centuries, scientists found the line spectrum of hydrogen atom and they were fascinated with its simplicity. This is the examples of the line spectrum of hydrogen atom. Bohr tried to explain the existence of the line spectrum of hydrogen later by assuming that electrons in a hydrogen atom orbit in a circular orbit around the nucleus and the energy is quantized. Then, Bohr came out with Bohr's atomic model based on three postulates. First, he assumed that the electron in a hydrogen atom can only be in permitted orbits of specific energies. Second, he assumed that an electron in a permitted orbit is in an allowed energy state and does not radiate energy and therefore does not spiral into the nucleus. And third postulate was energy is emitted or absorbed by the electron only when the electron changes from one allowed energy state to another. Energy is emitted or absorbed by electron in terms of photon. So I will explain these three postulates further later on. First postulate of Bohr's atomic model stated that the electron in a hydrogen atom can only be in permitted orbits of specific energies. The permitted orbits here refer to fixed pathway around the nucleus of an atom. For example, the fixed pathway n equals to 1, n equals to 2, and n equals to 3, n equals to 4, and so on around the nucleus of an atom. And these permitted orbits are of specific energies. Hence, these permitted orbits can also be translated into energy level diagram with n equals to 1 of energy level diagram corresponding to the specific energy of orbit n equals to 1, energy level n equals to 2 corresponding to the energy state of orbit n equals to 2, and so on. As you can see in the orbit diagram on the left, the distance between orbits are getting smaller as the orbits are further away from the nucleus. Hence, when we draw the energy level diagram, the distance between each level should be drawn closer as well. And at the infinity, because the energy differences between energy levels are too small, they seem to overlap with one another. Therefore, when we draw, we need to use bold line to represent overlap of many energy levels. Second postulate of the Bohr's atomic model stated that an electron in a permitted orbit is in an allowed energy state. This means that the electron in a permitted orbit possesses energy corresponding to the energy state of the orbit, and the formula used to calculate the energy of an electron in a particular orbit is energy equals to negative RH multiplied with 1 over n squared. And the RH here is referring to the Rydberg constant, which is equal to 2.18 times 10 to the power of negative 18 joules. And the n here is corresponding to the orbit or energy level of the electron. So, if an electron is at orbit or energy level equals to n equals to 1, what is the energy corresponding to the electron to be at that energy level? To calculate the energy corresponding to electron at a particular energy level, first we need to determine the energy level. For instance, in these examples, we have the electron at energy level n equals to 1. So what we need to do is we just need to substitute n in the formula with 1 to get the energy. So the energy corresponding to electron at energy level n equals to 1 is equals to negative 2.18 times 10 to the power of negative 18 joule. If the electron is at energy level n equals to 2, then you just need to substitute the n in the equations with 2 to get the energy corresponding to the electron at energy level n equals to 2. And this gives the energy equals to negative 5.45 times 10 to the power of negative 19 joules. If the electron is at energy level n equals to 3, then just need to substitute the n with 3 to get the energy of the electron at energy level n equals to 3, and this is equals to negative 2.42 times 10 to the power of negative 19 joules. From the calculations, there are a few things that you need to take note on. The first one is the lower or more negative is the energy of the electron, more stable is the atom. And from the calculation, the lowest or most negative energy is corresponding to the energy of the electron at energy level n equals to 1. And as the n or energy level gets larger, the energy increases or becomes less negative. The lowest energy state, n equals to 1, we also call that as the ground state. And the higher energy states refer to n equals to 2 or higher, and we call that as excited states. In Bohr's third postulate, Bohr assumed electron can move between allowed orbits by absorbing or emitting a photon. And the energy of photon is equals to the energy difference between the two energy levels. So the final energy level minus the initial energy level is equals to the energy of the photon absorbed or emitted. For examples, an electron at first is at n equals to 1. In order for the electron to move to higher energy level, for example n equals to 2, the electron must absorb a photon. When energy is absorbed by the electron, then the electron can move to the higher energy level n equals to 2. At higher energy level, for example at n equals to 2, the electron is unstable and therefore will move back to lower energy level n equals to 1 by emitting photon. And the energy of the photon we can calculate using the formula energy of photon equals to Planck constant h multiplied by nu, and the nu is referred to the frequency of the photon. And the nu can be calculated using the formula nu equals to c over lambda, where c is referring to the speed of light in vacuum and lambda is the wavelength of the photon. Movement or transitions of electron between energy level can also be used to calculate the wavelength of the photon using the Rydberg equation, where 1 over lambda is equals to the Rydberg constant multiplied with 1 over n1 square minus 1 over n2 square, whereby the n1 must be smaller than n2, and the Rydberg constant here is 1.097 times 10 to the power of 7 per meter. Using the energy of electron at particular energy level, we then can calculate the difference between energy level using the formula energy difference between two energy levels equals to Rydberg constant multiplied with 1 over initial state square minus 1 over final state square. And because here is energy, therefore the Rydberg constant value is 2.18 times 10 to the power of negative 18 joules.